My guest today is Professor Animashree Anandkumar, who's Professor of Computing and Mathematical Sciences at Caltech. Her research interests are in the areas of large-scale machine learning, non-convex optimization, and high-dimensional statistics. In particular, she has been spearheading the development and analysis of tensor algorithms for machine learning. Welcome, Anima. You have been working a lot on tensor algorithms, especially in the context of unsupervised machine learning. Could you talk a bit about that?
Example of why this is so effective. So think of like just looking at how many times the words occur in a document and trying to judge what the topic is. If I told you the word apple occurs in a document a lot, then you're not very sure, right? It could be the fruit, it could be about the company. If I only told you that information, it's not enough. But if I told you words apple and orange occur together, maybe, it's fruit, but then orange is also a company. But what if I told you apple, orange, banana, kiwi, lots and lots of different uh, information like that, then you are much more confident this document should be talking about fruits, even though you don't know any of the details. And so that's the idea. This high level topic information can be extracted by looking at co-occurrence of words, right? Like if lots of words co-occur, and you look at the spectrum of such tensors, where there is large energy, those directions should represent topics that are dominant in this document corpus. And so that's how we came upon the use of tensors for machine learning problems, for unsupervised learning problems. And since then, as the deep learning revolution progressed, what I realized is that tensors are very much at the core of next generation neural networks, right? Because if you think of the neural network, the basic structure is you take in the data, you do some matrix operations, right? Like could be just a fully connected layer, which is matrix multiplication. Convolution is essentially a very special form of matrix operation. But then there is no need to just limit to matrices other than the historical reasons. We built our foundation of math with linear algebra because we could prove a lot of properties. We had polynomial time algorithms where we knew converged to the right solution. But then long since we have abandoned that, right? Once we started neural networks, there are no guarantees of convergence. We are not sure what kind of non-convex optimization problem it is. Yet in practice, in so many scenarios, we can make it work. So in that new era, what we really need is also better primitives to build our neural networks, right? An entirely new class of neural network architectures. And that requires using tensor operations in different layers. So this way we can better capture the inductive bias of multidimensional data. Let's say you have video data, you could have like combination of video and LiDAR data in say autonomous driving. All this is highly multidimensional. And so you can better capture the structure using tensors in this. And that's what that paper gives an overview. We also have an open source framework called TensorLi. It's Tensor with LY in the end. It's open source. I encourage you to go check it out and use the GitHub repository. And we have notebooks there to really go line by line to explain all the concepts. So it's very easy to follow through. And what we made is very easy to program this, right? Without understanding any details of what tensors are or how to implement them, you can explore different kinds of tensor architectures into the neural network layers. And that's the ability that I think will be very beneficial because this way, what we've discovered is we can have now neural networks with tensors that are much more compact. Because of the inductive bias, we can make these networks smaller, but still are very robust and can generalize well. So you don't just need bigger and bigger networks, right? So that's one side of the field is moving towards that. If you look at large language models, but if we can like also have smaller models with good generalization abilities that can be very effective for, let's say, edge devices, being able to do this on small devices or reduce the power consumption of training these models. And that's where I think tensors can play a very important role.
So, I mean, I don't know a lot about this, but so is it correct to think about tensors it's a data representation, it's a matrix, right? So it allows you to sort of store information more efficiently, compress information. So you could have tensor inputs, you have tensor weights, and you have tensor outputs. So essentially, it's more of an efficiency issue, right, of the flow of information through the system.
Indeed, it's efficiency and also capturing the structure of data better, right? That's why it's efficient. And so tensors are really extensions of matrices to more dimensions, right? So matrices have rows and columns. You can think of the three-dimensional tensor as having now three axes, right? Like this. And then with more dimensions, you can't picture it, but you can certainly write this down. And yeah, so thinking of it as an array is just the basic representation. But what makes it powerful is how it operates, right, on objects. So just as with matrices, we can multiply them together, and that builds the foundation of linear algebra. We can take tensors and we can contract, which is extension of matrix multiplications to more dimensions. And so that helps us build good hardware primitives. And at NVIDIA, we're building QTensor with very efficient tensor contractions. And so that also makes it very efficient in a parallel system to run these methods.
And I guess it's extensible, sort of infinitely extensible, right, in some ways. So you don't really have a constraint that way.
That's right.
Could
That's
have
right.
dimensions
Yeah.
and can be very, very high if you would
Mm-hmm.
like. And so you think that the tensor-based methods will sort of go into hardware design ultimately? Because software seemed to have evolved a lot faster than is hardware keeping up, or what's happening on the hardware side?
Yeah, I mean, that's a great question, and with my role at NVIDIA as Director of Machine Learning Research, I'm always investigating the interfaces between hardware and software, right? And what we see is, the boundaries are much more blurred, right? Like if you think about CUDA as the platform, it's a software platform that really helps have all the primitives for efficient hardware utilization. And that's what I just mentioned also about NVIDIA QTensor, which gives hardware primitives for tensor contractions. And so we can now use that into packages like TensorLee or PyTorch or others to build neural networks with good hardware efficiency. So we always have to kind of keep in mind in terms of how to, right, also accelerate this on parallel hardware like GPUs. And to do that, indeed, we have to keep track of what kind of computational methods are effective and how to also parallelize them very effectively.
Yeah, I have another paper here, Secant, self-expert cloning for zero-shot generalization of visual policies. So generalization has been a long-standing challenge, you say, for reinforcement learning. Visual RL in particular can be easily distracted by irrelevant factors in high-dimensional observation space. In this work, we consider robust policy learning, which targets zero-shot generalization to unseen visual environments with a large distributional shift. So this has always been a problem with deep learning, right? So we could build beautiful models from the training data, but then each show it a picture that it hasn't seen before, it seems to fail. So zero shot generalization, meaning building something that's able to recognize something that it hasn't seen before at all, right?
Exactly.
So what is Secant?
Yeah, as you mentioned, right, like robustness is an issue with a lot of standard computer vision algorithms. And so now, on top of it, if you use this in reinforcement learning, so think of a self-driving car, right, that's using this computer vision system and trying to detect if there are pedestrians, if there are other cars, and suddenly there is a hailstorm, or suddenly there is, let's say, a sandstorm that it was never trained on. And then it can completely fall apart, right? Because now it's also part of the decision making loop. It's not just trying to recognize what's in the image. There are consequences to wrong decisions. And so that's what makes it a lot more fragile because even if it's slightly wrong in this, trying to build that into the decision-making loop can lead to catastrophic failures, right, in safety critical systems. And so what we wanted to investigate was, can we make reinforcement learning algorithms that use, right, like images, even high resolution images, and are robust to noises at test time. That's what we call zero shot generalization. So you can have all kinds of arbitrary noisy images at test time, even though training time, we didn't train for those specific noises. And that's the whole aspect, right? Like if you want to launch a self-driving car into the real world, we can't foresee every scenario. We can't foresee every kind of noise. And so that was the motivation behind this. And so the way we went about doing this is really a two-stage process. So what we, so because the idea is if you try to get the algorithm, the agent to directly learn on all kinds of different noises, right, at training time, it's just too difficult because it has to first try to learn what's in the image. It has to then do reinforcement learning, try to find a good policy and take a good action. All this is too complicated. The optimization landscape is too complicated. And so we did a two-tiered stage where, you first have what we call a teacher network that only learns on clean images. So, if you're given clean images, it drives perfectly well, right? It can, kind of drive smoothly, or whatever objective you give, it's able to achieve that. But then, it won't be robust to noise. But then in the second stage, what we have is a student, another model where it faces the noisy input. So it's given noisy inputs, right? If on its own it tries to do reinforcement learning from scratch, it's very hard to find a good policy of driving because it gets too confused. On the other hand, it now has the supervision from the teacher because the teacher has knows what to do under clean images, right? So if the image was perfectly clean, you would know how to drive very well. And so it's really helping each other, right? So this teacher is helping the student learn under the noise. And so this essentially is a more staggered approach to deal with noise, because if you try to feed in all the noise all at once and ask it to do reinforcement learning, that's way too complicated. And with this, we are able to now resolve many complex simulation environments. In the paper, you will see, the autonomous driving is one example, the robot manipulation in all kinds of challenging scenarios. These kinds of environments where you have certain decision making, but we add all kinds of, noise or right kind of distortions to the image to confuse it. It's still able to handle it like humans would have been able to do.
Yeah, that's very fascinating. To some extent, that's what the brain appears to be doing. Again, neuroscientists will be making a lot of noise. But we don't need a lot of label data to get reasonable decision making. And so we are able to take a noise, able to fill in missing information, and reach a reasonable decision. And so, if I understand this correctly, what you're saying is that if you train a neural network with clean images, you have sort of a starting point, and then you can feed in noise to it. It can take the existing heuristics and assign a probability, sort of filling in the gap, so to speak, assign a probability that it's going to go in one direction or the other. Is that the way to think about it?
Yeah, roughly. Because the idea is, like this clean network knows what to do if there was no noise. Now you're training another network, right, that has to deal with noise, but it gets the help from the network that has clean images. So it kind of knows what to do, rather than having to figure out on its own how to deal with noise and also come up with a good driving policy for them.
I remember reading in one of your papers, I think that, so, we always have experts in the domain, and experts have over long periods of time running repeated experiments, have heuristics. And we don't really have a robust way to get those expert heuristics into AI, right? So is this something that is there a sort of a systematic way to do that?
Yeah, that's a great question. And that's difficult, right? Because how do you have the human in the loop? How do you extract knowledge effectively? I think, a lot of it right now is in terms of like the experiments that are already done, right? And that was successful. We kind of bake in that information. But what's missing is all the experiments that didn't work. When I talk to, for instance, Frances Arnold, who's Nobel Prize winner here at Caltech for her work in protein engineering, right? She has so many intuitions of what would work for an experiment to go through and what wouldn't. So how do we capture that? I think that's still an open question. Because you can't have the human be engaged a lot, right? It would be too slow and infeasible. Yeah, that's to me one which I think is very difficult. But I do want to come back to the earlier point you made about lack of supervision for humans, whereas machines currently need a lot of supervision. An exciting area where we've seen a lot of progress in the recent years is called self-supervised learning. So where the model generates its own supervision, right? It doesn't need labels and human labels to begin with. And that, in many cases, has shown to be as good or even better than supervised learning models. And the intuition is if you can like figure out all the data transformations that leave the image unchanged. For instance, you rotate the image, you crop a little bit, right? You add this noise. We know it's still, if the cat is in the image, it's still the cat, right? And we're teaching now AI as well to know that it's still the cat, irrespective of all these changes we make to our input. And so that self-supervised learning method has shown to be very effective. So we are very close now to also resolving the issues of requiring large-scale supervision. In one of our recent works, we've been very excited to see how, just having like a bounding box supervision, right? So, like having a box around, say, my face, this is very cheap and easily available, right? On the other hand, if you try to segment parts of my face, especially tell where my eyes are, everything, that's much more expensive for a human to label and carefully trace out. And so in one of our recent works, we show you don't need all this very expensive supervision. You just need a bounding box. And that's enough for the algorithm on its own with self-supervised learning to figure out how to segment and how to do correspondence learning. So I think we are now much closer than ever to also doing away with a lot of human supervision, which are very unnatural, right? Like especially in domains like natural images, where if you know what are the transformations that keep the image the same, that don't change the perception of what's in an image, I think that's very powerful information to bake in.
Yeah, so brain appears to be very efficient in transformations. Um, and so you can think about translation of languages. They say accents is actually a function of a transformation the brain is doing if you loop in one culture and shift to another. And we appear to do this transformations in geometric shapes really easily. There is there isn't a way for neural nets to do that, right? I mean, if you flip a cat, yeah, it's going to get confused, so to speak.
Yeah, so right now, how we are trying to teach it is by giving it a lot of augmented data, right? You also give the flipped cat and say it is still the cat. And I think the way to get around this is really with 3D computer vision, right? Or, having like, like stereo vision like humans do, because without that, if it's just two-dimensional, there's no way for it to tell what's going on. Whereas we are in the three-dimensional world, and there's now a lot of new research being done to showcase how to do this.
Yeah.
So I
Yeah, go
do
ahead.
want to quickly come back to the earlier question of how to bake in the human knowledge in different scientific domains. It is a hard question, but maybe I can quickly give some examples of how we are approaching it at Caltech. The work we talked about at length earlier on partial differential equations, right? That was achieved with close collaboration with Andrew Stewart in applied math and Kaushik Bhattacharya in material sciences. So their decades of expertise and knowing what works, what are traditional methods, what's the shortcoming, and how to bake that into machine learning. So it's still very human driven, completely human driven, right? But I think that's the key for now. I think it's very hard to kind of design automated extraction algorithms directly from human experts. But if you get AI experts to work together with human experts, I think we can create a lot of magic.
Yeah. So I do some work in healthcare and life sciences and financial markets. And so I don't do anything with machines, but I do work with humans. And then humans are incredibly unpredictable, but they do have a lot of experience.
Mm-hmm.
And so our challenge ultimately is how do we combine sort of human expertise with artificial intelligence?
Mm-hmm. Mm-hmm.
And at the very tactical level, there is problems with consensus building. So, for example, physicians will always reject an AI opinion.
Mm-hmm.
They say, I know a lot better than any machine that you can ever invent, right? So there is a consensus issue, and then there is a question of assimilating human experience and intuition with
Yes.
machine learning. And I think if we can do that, I think it makes a huge difference in a very practical way.
Absolutely. And that's why I think these interdisciplinary collaborations are so crucial to solving these hard problems.
I want to touch on a few more papers. So, benchmarking few shot visual reasoning for human object interactions. So, visual relationship reasoning is central to how humans interpret the visual world, and there are many dedicated benchmarks, you say, for this task. Although significant advances have been made on these benchmarks, there exists still a gap between human level cognitive reasoning and machine level pattern recognition. So what do you mean? What do you mean by that?
Yeah, I mean, in lots of ways, right? I mean, we talked a lot about robustness, right? Being different in AI versus the human brain. The other is the ability to reason. Like, when I see your screen, I see the scientific sense, even though it's not the full word, because I know the context, I know that's what must be in the screen. Although I don't need to see the full question mark, I know it's the question mark, right? But I also have the totality of the screen because I know you're displaying this to popularize your podcast, which is great, and I'm so happy to be on it. Right, so we are kind of able to reason why you're kind of having this combination of shapes and images together. Whereas the way we do right now in AI is really pattern recognition, right? Whereas an AI model would maybe at best try to recognize you if it has that information or try to know that it's a human face, right? Get confused with what's in the background, what's contextual here. So that's what I mean by reasoning, not just try to just pattern match and say, okay, this is a human face or this is a cat. What is the totality of that image? What is it representing?
It's a context, right? It's a context that's missing. So do we have a way to incorporate context into machine learning?
Yeah, and that's what this benchmark is aiming to challenge the current AI algorithms to do, right? So not just look for specific objects, but also look at how they're related together, right, in the image. For instance, in my screen, you may see this is a mic, it's me, right? But why am I using the mic? I'm using it to make sure the voice quality is good. And if I have all these things behind me, it must be like an office environment, right? So it's all the context, but it's also relating all that context together. That's why we call it relational reasoning, because you're asking what is the relationship between me, a human, to this object, the mic.
Yeah. Um, I want to touch on another paper, Unitary N-Body Tensor Equivalent Network with Applications to Quantum Chemistry. I don't know much about this, but I'm particularly interested in this because I do some work in life sciences.
Mm-hmm.
And so, as life sciences, very big industry, very, very high attrition rates, very expensive to bring a drug to market.
Mhm.
A high percentage of that cost is really trying to find the right target and the right agent.
Mhm.
So do you think we have an application of AI in that context?
Certainly, the most invested area for AI in 2020 was healthcare, right? I mean, the pandemic accelerated it. I mean, everything from right streamlining the hospital process, which with COVID was very, very critical, to right discovering new drugs. There is so much potential. But as you said, drug discovery is a challenging area precisely because there's so many parts of the pipeline, right? And each one is very intensive either in computation or in the wet lab experiments. And so what we focused on in this line of work, which is in collaboration with Tom Miller at Caltech, who has the domain expertise, again, a great example of AI for science interdisciplinary collaboration, is to ask, how can we go to the quantum level, right? Like if we can predict the Schrodinger's equation, the ground energy state, right? Then we can predict almost all the properties of that molecule, right? How will it bind? How will it dissolve? What toxicity? So that kind of goes to the fundamentals itself to come up with these predictions. But then it's super expensive, so Schrodinger equations scales exponentially. So even having a molecule with tens of atoms will be much more than any supercomputer today can handle in a brute force way. And so what this line of work does is to ask, how can we build enough of the domain knowledge and the symmetries in the system, but still use neural networks to speed up the traditional approximations of Schrodinger's equations like the DFT or density functional theory to using AI methods instead, again, getting thousands of times speed up. But it's so critical to encode these symmetries, right, for better generalization. And so the rotational symmetry is an important one. You rotate your molecule, in the 3 dimensions, right? It should still be the same property, like the property doesn't change, the energy doesn't change just because you change your coordinate system. And the thing is, if you want to represent quantum features, you need tensor orbitals. The orbitals are represented through tensors. And so we came up with the general framework where you could have tensor inputs and you have symmetries in the system, and how does the neural network preserve these symmetries so that even as you change your input, the output correspondingly is equivalent according to the symmetry group. And so we built a general framework, but then we applied it to chemistry, and where we saw very good zero-shot generalization properties. So train on very small molecules for solving for the energy of, for in the quantum sense, and directly be able to generalize to larger molecules.
Yeah, that's really exciting. Basically at the heart of chemistry is physics, and physics is probably more generalizable. So, going back to our earlier discussion about, sort of expert heuristics in a place like Pfizer, for example, there are a large number of experiments run over 100 years. They have heuristics, expert heuristics. And so right now, the way this is determined, sort of the properties of chemicals is really based on those heuristics generated from large amounts of data and expert opinions to some extent, right? So if this is possible, this is sort of a digital high throughput screening, right? High throughput screening still takes a lot of time and a lot of expenses. But if we can evolve into sort of a digital high throughput screening, that is a huge paradigm change, I think, for life science.
Certainly. And that's the ultimate goal.
Do you have any sort of use cases that are practical in this arena?
So my collaborator, Tom Miller, has spun off a startup called Entos that is closely working with many pharma companies and coming up with promising results of good predictive capabilities for these methods. So yeah, I'm very excited to see more of that.
Excellent. Yeah. So in conclusion, Animas, so you're working on a lot of these interesting techniques in deep learning deep learning methods. They're sort of, I guess, two different opinions. One is, some people think that deep learning is sort of on a wrong track. And that's because, deep learning is nothing like how the brain works. And so some people believe that we're going to hit a wall, that we can't really go any further. And others believe deep learning would actually ultimately replicate the brain. So the other extreme. So where do you stand on the spectrum?
Yeah, I mean, I think to me there are so many practical use cases, right, where we can work with current machine learning methods, but certainly there are shortcomings, so we have to resolve them and improve them, build new foundations. So I would say somewhere in between.
Somewhere in between. Where do you think, if you look forward 5 years, where do you think we will make sort of the biggest leaps in this area? Um, I mean, there's a lot of speculation around this, but so where do you think we will come out, let's say, in 5 years?
Yeah, I think the next 5 years are going to be very exciting. I mean, personally, for me, AI for science is very exciting, right? Like now, finally, we're seeing the benefits of AI in core scientific domains, in drug discovery, I talked about, scientific simulations. On the other side of the spectrum, we'll also see AI moving more and more towards the edge. So being baked into tiny devices, not just big data centers, and with 5G and ultimately 6G connectivity, being able to have much more smart intelligence on edge devices and connecting them effectively. I think those are some exciting areas.
AI for Science is a Caltech initiative, right? So do you want to talk a bit about what that is?
Yeah, AI for Science is an initiative that I co-founded here to really increase these interdisciplinary collaborations across the campus. And because what we want is a way for AI faculty and students to systematically engage with experts across all areas of sciences, right? And to understand what kind of problems they're facing, why standard AI methods are not useful or enough for them, what else do they need? So those are the deep intellectual challenges. And with that, building new foundations for AI that's going to be very effective for the coming years. I'm very excited about this initiative.
Very quickly, one thing we didn't touch on is cosmology and astrophysics. And when I talk to folks in that domain, there's a lot of AI applications going on there. There is tremendous amount of data. We are, fast approaching a scenario where humans can really analyze this data. So, do you see applications there?
Oh, yes, so much of it. My colleagues here at Caltech and elsewhere, I talk to them regularly. I think the use of generative models like GANs has shown a lot of promise there. Like computer vision algorithms to easily detect, let's say, different kinds of, objects in the sky, like has been very effective. So yeah, I see a lot of exciting uses there.
Excellent. This has been great. Thanks so much for spending time with me.
Thanks a lot, Gil. I really enjoyed this.
Thank you.